Henderson-Hasselbalch equation is great for a lot of different things, but one of the main things it's useful for is figuring out at a given pH how much of something is protonated, that is in its conjugate acid HA form, versus deprotonated, that is in its conjugate base or A- form. The problem is how much of something, well, that can be expressed in a bunch of different ways, and you could be asked a lot of different questions about this. And unfortunately, the information that you can get directly from the Henderson-Hasselbalch equation is pretty much the least useful form. What it's going to give you is it's going to give you a molar ratio. It's going to give you a ratio of the concentration of your conjugate base over the concentration of your conjugate acid. Basically, it's going to tell you how many parts of conjugate base do you have per part of conjugate acid. So this is useful for like qualitative terms, like if you want to say, yeah, I've got tenfold more. So that's helpful, right? But what if you actually want to know, like, well, how much do you actually have in terms of concentrations or in terms of numbers of moles? Well, in this case, we're going to have to convert that ratio into a fraction and use that rather than use that direct ratio. And when we're doing this, we need to remember that basically we're talking about parts of A- per HA. And well, we have to take into account that when we want the molar fraction, that's going to be our parts of A- per total parts. So both your A- and your HA. It's like if you go shopping for some fruit and you get 2 apples and 1 orange. The ratio of apples to oranges would be 2 to 1. But the proportion of fruit in your basket that is an apple is going to be 2. So if you were to be given the proportion of apples to oranges, you would be told that it would be 2, but the proportion of apples would be 2/3. Similarly then, if you say we're told that the proportion of apples to oranges was 2/1, you could have 4 apples and 2 oranges. But you're given that simplified ratio, and so then you have to take into account that it's telling you the number of apples per number of oranges, so you're still told that value of 2. I think that the easiest way to kind of see this is with just like putting a number to things. So say you go ahead and you rearrange the Henderson-Hasselbalch equation to get this formula where we can figure out the molar ratio is equal to 10 to the pH minus the pKa. And note that this is the same thing as saying we're taking the anti-log 10 of pH minus pKa. We did that and we got a value of 2. Well, what this would mean was that we had 2 parts of A- per 1 part of HA. Therefore, if we want the molar fraction, we're going to have 2 divided by 2 plus 1, which will give us 2/3 or about 0.67. And we can easily convert this fraction or proportion to a percentage just by multiplying it by 100. And we can see that about 67% of it is in its deprotonated state, is in its conjugate base state. Similarly, if you got an answer of 0.5 for your molar ratio, that is not telling you that half of it is deprotonated. Instead, what it's saying is there's 0.5 parts of it deprotonated per part of it that is protonated. So if you want to figure out the fraction of it that's deprotonated, well, that would be 0.5 divided by 0.5 plus 1. So 0.5 divided by 1.5, and so we're talking about 1/3, about 0.33 or 33%. So we could get the fraction, and we can basically do this for no matter what our number is. We have this basic formula where we have the molar ratio, which I'm just going to abbreviate here, MR. I don't know if other people abbreviate it MR, but I find it helpful to kind of not have to look at this big bulky thing all the time. But basically, this is going to be what you're going to be figuring out based on your pH and your pKa using the Henderson-Hasselbalch equation. You can figure out this molar ratio. To figure out the fraction or the proportion that is deprotonated, well, then you just have to do the molar ratio divided by 1 plus the molar ratio. Because remember, with the molar ratio, well, that's parts of our conjugate base over 1 part of our conjugate acid. And so we have, if we want to find the fraction of it, we do the molar ratio divided by 1 plus the molar ratio. What if we want to find the fraction that's protonated? There are a couple of ways. One is if we've already found the fraction that's deprotonated, well, we can just subtract that from 1 because the fractions need to add to 1. Alternatively, if we didn't want to go and find the conjugate base first, what we could do is we could just do 1 divided by 1 plus the molar ratio, because now we're talking about the 1 part per all the parts versus those other parts per 1 part. We could also write this out with our 10 to the pH minus pKa, because that's typically where you're going to be plugging in. So typically I find it easiest to just find this 10 to the pH minus pKa value first, and then divide that by that value plus 1, divide 1 by that value plus 1. So that would give you the fraction. And if you want to find the actual concentration, well, then you just have to multiply that fraction by the total concentration of your acid to your base and your base, which is often what you're going to be given. So if you have a buffer, say you're told you have a 500 millimolar buffer, it's going to be equal to the total concentration of the acid and the base. And then you can figure out the amounts that are in each of these forms. And if you have the volume as well, then you can figure out actual numbers of moles. Let's go ahead and try out a few examples. As I mentioned, there are a bunch of different times that you can use the Henderson-Hasselbalch equation. We'll start with an example like we were just talking about, trying to figure out how much of something is protonated or deprotonated at a given pH. But there are other times you could use it as well, such as if you want to know how much weak acid and its conjugate base to mix to get a buffer at a desired pH. Or you want to know the pH if you're given the proportions of your conjugate acid or your conjugate base. So lots of different things you can do. The Henderson-Hasselbalch equation is great for a number of different reasons, and one is that it works even if the pH has been adjusted or altered by the presence of other acids or bases. And so we'll look at an example looking at, well, what proportion of histidine side chain is protonated at a given pH. Now, it doesn't matter why it's at that given pH. It doesn't matter what other acids that are in that mixture to give it that specific pH. All that matters is that, well, you know that pH. So it's really cool. Another thing about it is it can be used with concentrations or with moles. So here you see like these little concentration marks, but we can also use it if we just have moles. As long as they're in the same solution, the volume is going to be the same. And so they're going to cancel out. Because if we think about, well, what is a molar concentration? It's moles per liter. So if you were to say have moles and then you were to convert it into moles per liter, you would be dividing each of them by a liter. But then that would basically just cancel out, because what we're talking about here is a ratio. It can be a ratio of your moles, or it could be a ratio of your molar concentrations. And because it's just like this ratio, as long as those are in the same concentration, so it could be millimolar of both of them, or it could be molar of both of them. Often we convert things to molar just because some things need to be in molar. So in our first example, what percentage of hist has its side chain protonated at a pH of 7.4? So we're talking about the amino acid histidine, which has a pKr. So basically the pKa for its side chain or its R group is 6. And we want to know, okay, well, how much of that is protonated at a pH of 7.4? How can we go about this? Well, we can go and we can figure out the molar ratio pretty easily. So remember that we can figure out that molar ratio, our A minus to our HA, by taking 10 to the power of our pH minus our pKa. So in this case, what we're going to have is 7.4 minus 6.0. That's going to equal 10 to the 1.4. That's going to give us an answer of 25.1. Okay, so this is our molar ratio. It's telling us we have 25.1 parts of it that are deprotonated per part of it that is protonated. Our question is asking us about the parts that are protonated, but it's asking us a percent. So we need to do a couple of things. We need to change this into a fraction, and we need to kind of figure out for the protonated form, not the deprotonated form. So remember, if we wanted to figure out the deprotonated form, we would do 25.1 over 1 plus 25.1. But we want to know the protonated form, so we need to do 1 divided by 1 plus 25.1. So we have our molar ratio plus 1 because it's per 1 part, and then we care about that 1 part. So it's 1 divided by 1 plus 25.1. And if we do this, well, then 1 divided by 26.1, we get an answer of 0.038. So what is this telling us? Well, our fraction is 0.038, and we can easily figure out the percentages by just multiplying by 100, and we get 3.8% of it is going to be protonated at this pH. Every time you get an answer, you should do a little intuitive thinking. Does this make sense? If we're above the pKa, we would expect that since there's fewer protons available, more of it would be deprotonated. In this case, we are above the pKa, and our formula is telling us that basically we're having more of it deprotonated than protonated, since we only have like 3.8 of it, 8% of it in its protonated form. Alternatively, we could have solved for the fraction that was deprotonated and then subtracted that from 1 in order to find the fraction that was protonated. In that case, what we would do is we would take our 25.1 divided by 1 plus 25.1, and that would then give us a value of 0.962. And well, if we multiply that by 100, we get 96.2%. And well, 96.2% plus 3.8%, that's going to be the same. So we could have then subtracted this from 100%, or subtracted 96.2% from 100%, or subtracted 0.962 from 1. So either of those ways will get you that same answer of 3.8%. Okay, so now what if we want to actually find the concentration that was protonated? So what is the concentration of protonated His in 100 milliliters of 100 millimolar His at pH 7.0? How many moles of His are there? Well, we already figured out the proportion that was protonated. So that was our 0.038. So that's going to be the fraction. And now we just need to figure out, okay, well, what concentration is that correspond to? In order to do this, all we have to do is multiply this by our total concentration of His in both of its forms. So multiply that by our 0.1 molar. If we do this, well, now we end up with 0.0038 molar. So that would be the concentration of His in its protonated state. Now it's asking us how many moles there are. Well, if we remember that moles equals moles per liter, then all we have to do is multiply this by our volume in liters, so 0.1 liter, and we end up with 0.00038 moles, which we could also express as 0.38 millimole, or we could express it as 380 micromole. So you should get really used to going easily between these different units just by moving your decimal place. But that's how we can figure out the actual concentrations. Again, starting from just that Henderson-Hasselbalch equation, knowing the pH, knowing the pKa, and knowing the total concentration and the volume. So basically, if you have more information, if you have the total concentration, you can figure out the individual concentrations. And if you have the volume, you can figure out actual numbers of moles. But you're not going to get that information directly. Instead, directly, you're getting that molar ratio. One last example, something similar to what you might be doing in the lab to prepare a buffer, is figure out how much of the conjugate acid and conjugate base would you need to mix together to get a desired pH. So in this case, the example is asking us how much acetic acid and acetate, so our acetic acid, our conjugate acid, and our acetate, its conjugate base, how much of those would you need to mix in order to get 100 milliliters of 500 millimolar acetic acid acetate at a pH of 5.0? And it tells us that the pKa of acetic acid is 4.8. So let's think through our strategy. Remember, the information that we can get directly is going to be our molar ratio. And then what we want to do is we want to convert that into fractions. What we're going to do is we're going to find the fraction of the deprotonated. That's going to be the easiest to find. We only need to find the fraction of one of them, and we can figure out the other. So basically, we can convert that to a fraction. Then what we could do is we can convert that to moles. So we want to convert that to molarity. And now what we could do is once we have that in molarity, we can figure out the molarity of the HA just by knowing that those have to sum to our 500 millimolar. And then for each of these, we just need to take the volume into account to find the number of moles. Okay, so let's go ahead and solve this. So remember our molar ratio, that's going to be our parts of our base divided by the parts of our acid equals 10 to the pH minus pKa, so 10 to the 5.0 minus 4.8 equals 10 to the 0.2. And if we go ahead and we do that math, then what we're going to end up with is 1.58 parts of our conjugate base to our conjugate acid. So parts of our acetate per acetic acid. Now what we want to do is we want to convert this to a fraction. So what we just did here was we found our molar ratio. And now we want to convert that to a fraction. And remember that the way that we're going to do this is by dividing it by that number plus 1. So 1.58 divided by 1 plus 1.58. And this is going to give us a value of 0.61. So that's going to be the fraction of our A minus. So now we need to convert that to molarity. So all we have to do is 0.61 times our total concentration, our 0.5, is that's going to give us a value of 0.31 molar of our A minus. What about our HA? Well, here what we know is we know that the total is 500 or 0.5 molar. So we can just take 0.5 minus 0.31. And this is going to give us that our concentration of our conjugate acid, so of our acetic acid, is going to be 0.19 molar of HA. So that's molar, but we want moles. And so now remember, molar is just moles per liter. And so now we just multiply it by the number of liters. So we just multiply this by 0.1 liter times 0.1 liter. This is making it easy for us because we just have to move that decimal point. So we're going to get 0.031 moles of the acetate. And we're going to get 0.019 moles of our HA. And so then if we wanted to go figure out, okay, well, how would you actually do that in the lab? You'd have to figure out the molarity of your acetic acid solution that you're starting with, and you'd figure out the molecular weight of that sodium acetate or whatever you're using. Figure out how much of them you need to add in order to add the certain amount of moles, and voila. But this is the starting point, figuring out how many moles you actually needed. There's this equation called the Henderson-Hasselbalch equation that allows you to go between a pH and pKa values in order to figure out things like what proportion of an acid is in the protonated or deprotonated state, as well as to calculate how much of the conjugate acid and conjugate base to mix together to get a buffer of a specific pH. And so those are the two main functions we're going to talk about using it for, but there are other things that you could do with it as well. And we'll get into some examples and things like that. You can use the Henderson-Hasselbalch equation to figure out the actual proportions of things that are protonated or deprotonated at a different pH based on their pKa. It's also really important, though, to realize we don't even need to use the Henderson-Hasselbalch equation. So basically, for each pH unit away from the pKa that you go, you're going to get tenfold more of one form. And so if you go 1 pH unit above your pKa, well, now we're saying there are fewer free protons around. That cookie jar is more empty. So you're less likely to find things being protonated. You're more likely to have things in the deprotonated state in the 1 pH unit above. If you go 2 pH units above, well, now you're going to have 100-fold more of it in the deprotonated state. 3 pH units above, 1,000, 4, 10,000. So you can see that by the time you're a couple pH units away from the pKa, it's predominantly going to be in one form. And if we go the other direction, if we go below the pKa, well, now there's more protons available. So now we have like the opposite situation. We're going to get tenfold more of the protonated form, and then 100-fold more, and then 1,000-fold more, and then 10,000-fold more. So if we're a couple units away from the pKa, we don't even need to use the Henderson-Hasselbalch equation to know that almost all of it is going to be in one state. But we can use the Henderson-Hasselbalch equation, and we will use the Henderson-Hasselbalch equation